I'm honored to present our work, Flexible Isosurface Extraction for Gradient-Based Mesh Optimization. This is a joint work with my colleagues at NVIDIA. Isosurfacing is a technique that extracts the surface mesh from a scalar field. Existing work like marching cubes mostly focus on reconstruction from a single, known field. However, in our work, we consider a different use case of isosurfacing, which is gradient-based mesh optimization. Specifically, we want to iteratively optimize for 3D mesh by representing it as the isosurface of an unknown scalar field. Our key contribution is to introduce additional parameters into the extraction scheme, which are updated along with the scalar field to better facilitate mesh optimization. So this paradigm for automatic mesh generation is becoming increasingly popular due to its ability to combine the strengths of both implicit and explicit representations. On one hand, it allows objectives to be directly evaluated on meshes, which could range from a re-rendering loss from a differentiable render to more complex mesh-based energy functions, or even loss from a physics simulator. The loss evaluations can be more efficient by taking the advantage of hardware-accelerated renderings and solvers dedicated for meshes. Further, it outputs mesh that are compatible with standard creativity tools like Blender and Omniverse. On the other hand, the surface is parameterized and updated in the implicit field, providing the flexibility to optimize over meshes of different topologies, like changing from a sphere to a genus 1 torus. A proper isosurfacing method can also act as a remeshing step at every iteration to avoid topological errors like self-intersections or inverting triangles. So these two issues are typically the stumbling blocks for prior methods that optimize a mesh from deforming a fixed template. Lastly, it is straightforward for a neural network to fit or predict an implicit function, making this approach especially well suited for machine learning algorithms, tasks, or mesh generation. So with all the nice properties of both implicit field and meshes, we need a capable isosurfacing method in order to fully leverage these representations. Specifically, in the forward pass, the extracted mesh should be of high quality, meaning it should precisely capture the underlying geometry in the implicit field without too many triangles or topological errors. During the backward pass, differentiation with respect to the mesh needs to be well defined, such that the scalar field would converge effectively in practice with this gradient applied to it. However, this is not the case for prior methods. Here we compare different isosurfacing methods for mesh optimization. Starting from a sphere initialization, we optimize the extracted mesh towards the ground truth mesh using multi-view depth supervision. These methods either diverges during optimization, like the do methods on the top, or fails to capture sharp features and producing many sliver triangles, as those marching grid method shown at the bottom. Therefore, we present FlexiCubes. It introduced additional degrees of freedom to adjust the mesh geometry and connectivity. This facilitates better fitting of surface features with nicely shaped triangles, and also enables well-behaved differentiation. FlexiCubes serve as a drop-in replacement that improves the result in a range of applications, including 3D reconstruction from both multi-view images and animated sequences, generative 3D modeling, physics simulation, and topological optimization with respect to energy function. Next, we will discuss a commonly used extraction method to understand their shortcomings and motivate our proposed approach. Prior works mostly adopt marching cubes and its generalizations like marching tetrahedra. So in grid marching, mesh vertices are extracted along grid edges where the linearly interpolated scalar functions changes sign. The gradient on mesh vertices can be back-propagated to the scalar field by auto-differentiating through this linear interpolation formula, which is well defined during extraction. However, the mesh vertices can only lie along grid edges. This prevents the mesh from fitting to sharp features. A workaround is to increase the grid resolution, but typically this is non-ideal for the optimization setting because it results in a large number of small triangles in low curvature areas. This adversely affects the downstream applications. Moreover, the cubic scaling of SDF queries with resolution creates a computation and memory bottleneck, especially in neuroimplicit, where each query requires heavy network computations. So how can we build a better isosurfacing method designated for optimization? Our key insight is that instead of improve the fitting with more elements, why not we give each vertex additional flexibilities for local adjustment? Moreover, because marching cube vertices has well-defined gradients, we want to express the dual vertex as a linear combination of primal vertices to overcome the divergence issues when optimizing with prior dual methods. To achieve this, we introduce three types of parameters, including interpolation weights to position dual vertices in space, and splitting weights to control how to split quadrilaterals into triangles. This is needed because the raw output from dual methods are quadrilaterals. We also borrowed the grid deformation idea from prior work to align the grid with thin features. Note that these parameters can be appended as additional output channels in the neural implicit, so we neither increase the number of queries needed or the elements in the resulting mesh. The interpolation weight include alpha, which adjusts the interpolation along each edge, thereby relocating the previous marching cube vertices. There is also beta, which computes the dual vertex based on the weighted average of edge vertices. Together, they intentionally parameterize the dual vertex as a convex combination, and therefore the mesh vertices is free to move within the convex hull of its grid cell vertices. When the cell emits multiple dual vertices, they lie in non-overlapping convex halls bounded by the corresponding marching cube faces. Because those faces are non-intersecting, this prevents nearly all self-intersections during optimization. Also, alpha and beta are constrained to be positive. This preserves the gradient directions back to the scalar field. The output from dual methods are typically non-planar quadrilateral faces, which are further triangulated for rendering or other applications. So in this example, you can see there's a clearly favorable triangulation by connecting vertices along the vertical diagonal because they align better with the curvature. An arbitrary split can cause artifacts in the curved regions. We therefore introduce another parameter gamma to make the choice of split also flexible and can be optimized as a continuous degrees of freedom. Specifically during optimization, gamma interpolates the surface between two possible splits and it converts to the one that minimizes the objective functions. Thus at inference, we can simply split along the diagonal with dominant gamma. Here we use one example to demonstrate the effect of each set of parameters we added in FlexiCubes. Adding the interpolation weights allow mesh edges to align much better with the sharp geometric features. This is further improved by allowing the grid to deform locally. Finally, with the flexible quad splitting, FlexiCubes can learn the right split, which removes the artifacts in the curved regions. Lastly, for applications like physics simulation and character animations that operates on TETMesh, we can extend FlexiCubes to tetrahedralize the entire volume on the fly, which also supports auto-differentiation. FlexiCubes can also extract mesh from auxiliary grid to obtain hierarchically adaptive meshes, so we can increase the spatial resolutions in area of high geometric details and reduce the triangle counts from flat regions. Now let's test FlexiCubes by plugging it into mesh generation pipeline. A recent work NVDiffract jointly optimized shape, material, and lighting from images. By simply replacing the isosurfacing method with FlexiCubes in the topology optimization step, leaving the rest of the pipeline unmodified, we observe improved geometry reconstruction at equal triangle count. Moreover, the reconstructed 3D models can be readily used in creativity tools like in Omniverse and support simulating robust physical interactions with virtual objects. Rather than fitting a single shape in the reference pose, having a surface mesh allows us to differentiably skin and deform the mesh and simultaneously optimize with respect to the entire animated sequence. This helped to redistribute triangles and avoid artifacts from mesh stretching. The extension to extract tight mesh allows us to combine the FlexiCubes with differentiable physics simulator and the differender to jointly recover 3D shapes as well as physical parameters, such that they reproduce the motion in the reference multi-view video under the simulation. Besides reconstruction, FlexiCubes can serve as a plug-and-play differentiable module in a 3D generative model and produce significantly improved mesh quality. Lastly, we apply a developability term on the extracted surface to encourage fabricability from panels. FlexiCubes has the freedom to fit the shape and satisfy the regularizer, whereas Marching Cubes does not. Thank you for listening. Check out our project page for additional results and learn more details.